Okay, so on this question, it says, this problem is based on a famous mistake made by 95 out of 100 doctors who were asked a similar question, and 95% of them got it wrong. The doctors were getting confused between these two questions: the probability of a positive test results given that a disease is present, and the probability a disease is present given positive test result. Those sound very similar. The doctor's mistake is called confusion of the inverse. The order of a given statement really matters. It makes a big difference. So pay close attention to the given statements made in this problem and their order. So that's what it's all about. And that's a very common mistake, even among the highly educated, like medical doctors. That's why this became kind of a famous statistical question, because 95% of doctors got it wrong when asked about it. And it's a medical thing. It's just a confusing statistical medical thing. So the order of a given statement matters. Confusion of the inverse. The doctors thought you could switch it around and it didn't matter. At least 95% of them thought that. And so let's try to get it straight. So here we go. Let's go through it. Suppose that in the United States, it was found that 4% of the population have a certain disease. Now you're going to have a different percentage than me right there. But the medical tests for this disease are not perfect, as we know, right? We're in the COVID days right now. We know that things aren't always perfect. Suppose further that if someone does not actually have the disease, that he or she still has a 30% chance of testing positive, what's called a false positive, right? They get a positive result even though they don't have the disease. Also, if someone actually does have the disease, he or she only has a 70% chance of testing positive for the disease. So there's a 30% chance of getting a false negative. Now you're going to have different percentages than me. So we know about, especially in these COVID days, we know about false positives and false negatives. Well, how does that affect statistics when it comes to actually, diseases and knowing whether you have the disease or not? Okay, well, here's the most important part of the problem for us. Note, you are going to need to make a table to answer the following questions. Start with a population of 1,000 people and fill in the table according to the above facts, and then answer the following questions. Here's the question. Given all this information, if a person takes a medical test that comes out positive, so if you go to the doctor, you test for this disease and it comes out positive, given all this information about chances of false positives and false negatives and all that stuff, what is the probability that you actually have the disease, that he or she actually has the disease? Right? Your answer is a decimal, 4 places. And then there's the vice versa. Finally, if a person takes the medical test that comes out negative, what's the chance that he or she really doesn't have the disease? And maybe that's a false negative. How do we answer that? So that's what we're looking at here on question number 1. A lot of information being given. We've done givens already. We know how to do givens. This is a more complex given. So let me bring the question over here where we can see it a little bit better. And all right, let me show you. It's all about that table. So let me come on down and make the table with you that they're talking about. This is going to be the most important part of the problem, is making this table. So to make the table, I'm going to go like this. All right, and I'm going to put on one side whether you actually have the disease or not. Disease, yes or no. Do you have the actual disease? Do you have, oops, there's a mistake. Do you have the actual disease, yes or no? And then up here, I'm going to put, does the medical test, the test result. The test result, positive, negative. So we got to make our own table, okay? And then of course on the outsides, we have the totals. Total here, total here. And in fact, I should probably just add that to the table. Oops. Shaky there. Like that. And like that. There we go. So put the totals on the outsides. Okay, and they're saying just go ahead and start with 1,000 people. That's what it's saying. Now you might wonder, well, how do you just start with 1,000 people? Well, it's just all percentages and parts, right? So like if somebody told me, 20% of the crowd is wearing hats at the ball game, I could say, well, then if there's 1,000 people, that would be 200 people wearing hats. Or if there's only 100 people, that's 20 wearing hats. Or if there's 10,000, you can do whatever numbers you want and then just work with percentages in the end. Does that make sense? I'm saying, suppose there's 1,000 people tested. I don't really know how many people they tested. It really doesn't matter because in the end, I'm just going to be dealing with percentage answers, which means part of the whole. So I can make up whatever total number of people I want. Does that make sense? Like here, I want that to really make sense and not just be something Mr. Heron says. So if I told you there's 70% of the people wearing hats at the ball game, and then how many, what percent were not wearing hats? Well, you already know it's 30%, of course, you're right. But I could do it with a number. I could say, well, suppose we have 1,000 people. If we had 1,000, and I don't really know we had 1,000 people at the game, but if 70% of 1,000, if you multiply that in your calculator, you're going to get 700 people wearing hats. Well, if there's 1,000 people, then 1,000 minus 700 equals 300 had no hats. And then I could figure out what percentage that is. I could say, okay, well, then that would be 300 out of the 1,000 is not wearing hats. And I would get 0.30, which is 30%. Now I know you're thinking, well, that's a terribly long way to get the problem. I know it is. But I'm just telling you that would work. Even though you think, well, you did 1,000. Yeah, I could have done any number. I just want to show you the truth of making up a large number. When you're dealing with percentages, you can make up any total number you want. Get that many hat, if 70% of the crowd was wearing hats and there were 1,000 people, then that would be 700 hat wearers. And that would leave 300 not wearing hats, and 300 out of the 1,000 would mean 30%. So as long as you just give a percentage answer in the end, it doesn't matter what total number of people you used in the middle. It's irrelevant. The percentages mean the part of the whole. And that'll come out the same no matter what you assumed the whole was. Okay, now why am I doing 1,000? A big number makes it easy. You'll see as we go. So just start with 1,000 people. That's what it said right here, right? I'm just doing their suggestion. I wrote this, my suggestion right here. Okay. So how do we do the rest of this problem now? So the rest of this problem, let's go through these facts very carefully. Let's read them very carefully. Suppose in the United States, it was found that 4% have the disease. Okay, we got to use that. Fact number one. Let me write that out for us. Down here. Fact one. 4% of everyone, 4% of the United States have the disease. Now you're going to have a different percentage than me there. Okay, what do I do with that? Well, that means 4% is 0.04, change it to a decimal, times 1,000 equals 40 people. Why am I doing that? Because that's 4, remember of, so 4%, 4% is 0.04, of is times, remember we've talked about that before, of is time, of the United States. Well, I just assumed 1,000 people. So I'll just, instead of United States, I'll just say group. 4% of the group. I assume the group size was 1,000 people. We know the United States is not 1,000 people, but I'm just assuming that. What is the United States like? 350 million, I think, something like that. 300 something million. Anyway, I'm just saying, suppose it's 1,000 people. So 4% of the group, 0.04 times 1,000 equals 40 people have the disease. You with me? So if we're talking about a group of 1,000 people and we know that 4% have the disease, then 4% of times 1,000 would be 40 people have the disease. So I can come up here. Where does that 40 go? Right there. Do you see that? Because that's the actually have the disease. Yes, total 40 people. And how many don't have the disease? 1,000, take away 40, 960. don't have the disease, right? Because these have to add up to be all 1,000 people. So if 40 have the disease, then 960 out of 1,000 don't. Tracking with me? You see how I'm coming up with those numbers? I'm saying if we're talking, I'm just going to take a random group of 1,000 people. And if I'm told that 4% of the whole United States has the disease, then that would mean 4% of any random group, about 4%, to grab 1,000 people at random, about 4% of them are going to have the disease. 4% of times 1,000 is 40 people. So 40 people out of 1,000 are going to have the disease. 960, subtract from 1,000, are not going to have the disease. Good so far? Now, come on down. What's the next fact? Down here. Suppose further that if someone does not actually have the disease, that he or she still has a 30% chance of testing positive. Wow. Let's write that down. That's fact number 2. If someone does not have the disease, still 30% chance of testing positive. So the 30% of that's a false positive, right? Now you're going to have a different percentage than me. That was my percentage. Someone does not actually have the disease, they still have a 30% chance of testing positive. Okay, so that means 30% of the people, 30% of the people that do not have the disease. So who is that? 30, that's 0.30 times, remember, of is times, 30% of the people that do not have this. How many people do not have the disease? In my case, that's the 960, right? 9 out of 1,000, 960 do not have the disease. That means 30% of them, 30% of the 960. Multiply that on your calculator. I'm getting 288 are going to test positive, even though they don't have the disease. So that's going to go right here, right? They test positive, but they do not have the disease. Are you seeing that? They test positive, but they do not have the disease. Right? That's what it said. It said 30% of the people that do not have the disease. 30% of the 960 times the 960, 288 people are going to test positive out of this group. Now, we can find the blank that's missing right here, because these have to add up to there's 960 people total that do not have the disease. Some test positive, some test negative. They have to add up to equal 960 people, don't they? So I'm going to take 960, subtract 288 right here in my calculator, and I'm getting 672. So these two add up to 960 now. All right, fact number 3. Last fact, and then we're ready to answer some questions. Also, if someone actually does have the disease, he or she only has a 70% chance of testing positive. Fact 3. 70% of those with the disease test positive. That's what it said, right? So that's 0.70 of is times those with the disease. Well, how many have the disease? Yes, disease, 40 people. In my case, in my example, 40 people. 40 people have the disease. So 70% of 40 people, that's 28. Use your calculator. That's 28 people. 28 people have the disease and test positive, right? They have the disease and they test positive. So let's go put that in up here. That's right here, isn't it? Right? They test positive and yes, they have the disease. But that leaves a chunk here, subtract, right? 40 minus 28. That leaves 12 that test negative. That adds up to equal all 40 people. So this now, and we can also add these up, total down here, right? Come on down here and I'll go 28 plus 288 equals whatever my calculator says. So I'm adding up my table. See how I'm filling out this table? 316, and this is 12 plus 6. I'm just adding. I'm adding down and adding down, right? Because that's the total positive, right? These are totals at the bottom and totals on the right, like we always do with these tables. And I'm getting, this is 684. All right, so we're able to figure out, to fill out, I should say, the whole table. Now we can answer the questions. So what questions are we going to answer at this point? Well, we're going to come in and we're going to answer their two questions. Their first question is, given all this information, if a person takes a medical test that comes out positive, what is the probability that he or she actually has the disease? All right. So what are they asking? Let's be clear on this. If a person takes the test that comes out positive, what's the probability they actually have the disease? So what's the probability they have the disease given the test is positive? Do you see that that's what's being asked there? That's what those words are saying. They're saying the person takes the test and it comes out positive. So we're given that. We know that for sure. They did test positive. And here's the question. What is the probability he actually has the disease? So what's the probability you actually have the disease given you test positive? So you go to the doctor, you test positive. What's the chance you really have the disease? It's not 100%, is it? Could be a false positive. So what's the chance you actually have the disease if you test positive? Well, remember, we've learned how to do givens. How do you do a given question? You circle the given part, test positive. You come down here and go, okay, where's the test positive people? Oh, it's this right here, test positive. These are all the people that test, right, positive. It's all these, it's none of these people. Forget about all these numbers. Forget about all these numbers. Why? Because they're people that tested negative or the total of the positives and the negatives. We don't care about that. We're just right now on this particular question, we're focused on only the people that tested positive in our table. That's what they said. Remember, that's what you do with given. Whenever they give you something, right here, it says given they tested positive. Right? Given that they test positive. So we're talking about that group of people. Out of this group of people, what's the chance you actually have the disease? Yes, it's the 28 out of the 316. Forget about all the other numbers, right? Whenever they do given, that narrows your focus to just that group. We're given that we definitely did test positive. We went to the doctor, we tested positive. That means we're in this group of people. We're out of the 316. What's the chance we really have the disease? 28 out of 316. 28 people out of 316 in the test positive group really have the disease. 28 out of 316. So I'll divide that on my calculator. 28 divided by 316. And I'll round my answer to 4 decimal places. And I'm getting 0.8. No, not getting 0.0886. Look at that. That's only an 8 or 9%. If you rounded that to a percentage, that'd be like 8.86% or about 9%, right? In other words, if you test positive for this disease, you only have about a 9% chance of really having it. That's crazy, isn't it? You go to the doctor, you test positive, and you've only got you have a very low chance that you've actually got. How did that happen? How did that happen? I thought that, I thought there was this false positive. Where was false positive up here? False positive. There's a 30% chance of testing positive. I thought only 30% of the people had a false positive. So then shouldn't that give you a 70%? If you really got a positive test result, isn't there a 70% chance you really have it? If only 30% are false positives? Well, no, it's not quite that simple. It's the other way around. Yeah, the probability that you're going to test positive if you have the disease is 70%. But that's not the same as the chance you're going to have the disease if you test positive. That came out very, very different, didn't it? You see that? That's where the doctors got confused, and they were way off in their thinking. They did not understand the implications of these numbers. Let's do the last one. I'll say a couple more words and we'll be done. So the last one is basically the same kind of question, vice versa. It says, a person takes a medical test, comes out negative. What's the probability that he or she does not have the disease? So it's just the reverse. So it's the problem. So if you go to the doctor, it says, nope, you don't got it. What's the chance that's really true? Probability that you do not have the disease given the test came out negative. So again, we've got to circle what's being given. The test came out negative. So now we're circling this group and ignoring all the other numbers, because now we're talking about people who tested negative. We went to the doctor and we tested negative. So we're among these 684 people that tested negative. What's the chance we do not have the disease? 672 out of 684. It's a chance we do not have the disease. 672 out of 684 in the negative category do not have the disease. 672 out of 684. Divide those on your calculator. And I'm getting 0.98245, so I'll round it to 25. So very likely, we have a 98% chance that we really don't. If we tested negative, that we really do not have the disease. Very likely. That one's not so surprising. The surprising one is this previous answer. Let's absorb that again for one more minute. Do you get what's going on there? And let me mention, this is exactly what I'll give you on the exam. This will for sure be on the next exam. And you can do it. It's all about making this table carefully. And I'm glad to help you on office hours, Zoom, whatever, to get that table done. It's all about practicing carefully making that table. It's an excellent exercise in thinking carefully about given statements. Very good exercise. But again, let me let the big picture land on you for just a minute. This is why the doctors got confused. Come back up here for a minute. False positive, right? Let's read this again. What does this say right here? This says, look at it carefully. If someone does not actually have the disease, okay, they don't have the disease, he or she still has a 30% chance of testing positive. So the probability that you're going to test positive, given you do not have the disease, is 30%. That's what they're saying, right? If someone does not actually have the disease, we're given they don't have the disease, he or she has a 30% chance of testing positive. Test positive, given they don't have the disease, 30% chance. That's a false positive, right? They tested positive, but they don't really have the disease. So you would then think, wouldn't you? Well, then doesn't that mean this question down here? Probably that they have the disease if you test positive. Well, notice that's switched around from these two, right? Disease is now in the front, test positives in the back, and the answer is wildly different, isn't it? It's only 9%, 0.0886, 9% chance. Do you see how hugely a false positive can end up affecting somebody who does test positive? You only have a 9% chance of having the disease. That's different than a false. You think, well, yeah, the false positive rate is 30%. So that means you test positive, you have a 30% chance of having it. No, that doesn't. That doesn't. That's a switch around. That's where the doctors got confused. You can see why. It's not simple, is it? Even for a medical doctor. I want you to know better than the doctors know. I want you to understand percentages and given statements and not be confused by the confusion of the inverse. The order of a given statement really matters. It's different to say, given not have the disease, what's the chance you test positive versus disease, chance of disease, given you tested positive. And this is the one we would care about in real life, right? You go to the doctor, they do a test, they say, hey, our test came out positive. We think you have the disease. Well, there's actually only a 9%, don't get all worked up. There's only a 9% chance you have the disease, very low, even though you tested positive. You see, that's important numbers that affect our lives, doesn't it? Don't they? This matters. So I'm glad to think about this with you if you're confused, but there's how we solve that problem.